Everyone. Okay. Oh, I confirm. Could you hear me well?
Yes.
Thank you very much. Thanks for joining and thanks everyone for coming here. Today's seminar will be on quantifying nature-based risks and opportunities, a novel metric for assessing ecosystem integrity and its economic impact. Work co-authored by a group of rather like young economists at Prometeia. And the paper will be presented by Stefano Tripodi. Stefano, a few words about Stefano. He's a senior economist at Prometeia Group, and he's specifically part of the economic forecasting and analysis group. His current research focus on the link between nature and economics and the study of nature-related risks, among which today he will be presenting one. Before joining Prometeia, Stefano was a resident researcher at Nova Africa, Lisbon, Portugal. Stefano has done his PhD in economics from Copenhagen Business School, Denmark. Thanks again for being here. We look forward for your presentation. You have 40 to 45 minutes for presentation. We will have 15 to 20 minutes Q&A session afterwards. For those of you online, please put your comments and questions to Stefano on the chat box, and we will collect and present to him to answer. And if you want directly engage or ask him, you can also do so. Thanks again for being here. The floor is yours, Stefano.
Thank you very much. Thanks a lot for the introduction, and thanks for having me. It's a pleasure to be here presenting my work. So apologies for my voice. I lost it over the weekend, so I will try to speak a bit loud. As Amsalu said, this is a paper co-authored with Benedetta and Giacomo, and the title is Quantifying Nature-Related Risks and Opportunities, a novel metric for assessing ecosystem integrity and its economic impact. If you prefer to ask questions while I'm talking, please interrupt me at any time. I have no problem with that. Okay, so what I'm gonna try to do today is to give a brief introduction on nature and nature-related risks, and then introduce some sort of index that we try to build, and then to do a bit of analysis with this index, try to, and try to estimate and see link some economic variables to the index that we build. The starting point of this talk is the recognition of the fact that nature-related risks are getting very, people are starting to talk about in the public debate, and the recognition is rising. And the interesting thing is that we moved from a purely climate change related debate to a public debate, which also includes the nature crisis, nature degradation. And we are starting to realize, maybe some of us already started a while ago, but in the public debate, we began to realize that there is a very close connection between nature and change, and we cannot forget about nature when we talk about these about risks. Ecosystem degradation and biodiversity loss involve negative economic impact and negative effect on financial stability, as pointed out by the Network for Greening the Financial System with in 2023. And as a response for this increasing recognition, there's been the establishment of global policy frameworks, which include the UN Sustainable Development Goals and the UN Convention on Biological Diversity, where it's stressed that preservation of ecosystem is essential for economic development and for supporting human well-being. From the macro to the micro perspective, also firms are increasingly worried about nature-related risks, and as such, they began to incorporate nature-related risks into enterprise risk management through the work of the Task Force on Nature-Related Financial Disclosure, which mirrors the TCFD for disclosure and risk identification, and so on and so forth. But even more surprisingly to me is that if we look at the latest World Economic Forum Global Risks Report, and we look at the risks that are perceived to be material and salient in the long run, we can see that each sector of society places nature as among the top risks. So there is a worry that nature and nature degradation in particular will be a risk that we'll have to face in, I mean, they call it the long run, it's the next 10 years, right? And if you look at this ranking, yeah, I mean, even the private sector places biodiversity loss and ecosystem collapse as the second most important risk that they foresee in the future. If you look at this ranking, it's interesting to see that in the top 5 position, there's a lot of green. So there's a lot of nature and climate related risks that are perceived as important and as relevant for, as I said, many parts of society. Another example of how these kind of risks are becoming, the debate is becoming more common is that the financial institutions such as the European Central Bank began to study nature-related risks as well. This graph is adapted from a paper written by Woldie and co-authors in 2024, where they study what is the impact of the European economy on nature and what is the impact of nature degradation on the European economy. And what they point out is that about 72% of the Euro area economy depends on at least one ecosystem service, that nature degradation is something that is real, nature is subjected to numerous human pressures, and this degradation poses a material risk for the economy, because the economy and the financial system are vulnerable to nature degradation and contribute to it. And as such, they claim that it's important to identify risks and assess the economic and financial impact of these risks. The problem with nature, or maybe the nice part about nature, is that nature is very complex. And nature is, the natural world is based on relationships that are very complex, that are non-linear. Think about tipping points where at some point the ecosystem completely collapses. And it's also dynamics. And this is an issue when we try to understand and to model and to capture some components of nature using maybe just one indicator, because a single indicator can hardly capture this complexity. So the main part of this paper, what we do is to try to propose a new indicator, or which we call Ecosystem Condition Index, ECI, which is basically a combination of different indicators, which tells us something. Each indicator gives us an information about the status of ecosystems and nature. The 3 measures that we use are the species abundance, the number of species at risk, and the forest landscape integrity index, which gives a measure of how pristine a forested ecosystem is. And the nice part is that we can do this on a spatial level. So we can calculate this index using a very fine grid. Which is very nice because we can really go local and study what is happening at the local level. So the 2 questions that we try to answer in this paper are the following. So what is the relationship between ecosystem conditions as proxied by our index and agricultural productivity? We focus on agriculture because we start with agriculture, because when we think about ecosystem services, I mean, at least to me, one of the things that comes to mind is the fact that agriculture is related to ecosystem services in several ways. Think of, I mean, the most common one is crop pollination, of course, whereby pollinators are necessary for growing crops, but also water retention, the soil quality, and so on and so forth. And there's been research that demonstrated the economic benefits of a high environmental quality when it comes to agricultural productivity. And the second question is we are trying to look into is to understand what are the channels that through which a condition of nature, a condition of an ecosystem affects the economy. And with the economy, I mean agricultural productivity, of course. It could be that, you can think of a production function where you include nature as a productivity shifter. So more nature makes your factors work better and you produce more using the same quantity of labor and capital, for example. But you can also think of a world where the connection between nature and climate is as such that nature can shelter the economy from economic losses from climate change, and nature degradation can amplify these damages, right? So we are trying to see if this is a possible channel. And I'm just going to give you a preview of the results that we have in the paper, and kind of like what we do in 4 points. We use this information on different ecosystem characteristics to we combine them, and we try to make a proxy which should give us information about the ecosystem conditions and also about the ecosystem productivity in terms of ecosystem services, right? And when we do that, we find that using a combined index, an index that combines different information, we can better predict other individual ecosystem characteristics compared to a situation where we only use one. So this adds, combining different indicators adds information, let's say, which is good. Otherwise, we would be just using one index and the whole thing would be useless. We try to estimate the elasticity of agricultural productivity to ecosystem condition loss. We find a negative correlation between our indicator, the ECI, and agricultural gross value added per hectare of cropland, which highlights the importance of, highlights the economic risks that are associated with nature degradation. We show that the effect of a loss in the ecosystem conditions, or the effect of ecosystem degradation, is not constant across the productivity distribution. And actually areas that have low productivity, low agricultural productivity, are somewhat less affected by nature degradation, whereby areas with high agricultural productivity are much more affected. And also we try to test whether nature has a positive role in sheltering the economy from climate damages. And again, what we find is that areas that experience less ecosystem degradation are less at risk to, in this case, temperature extreme, but you'd say climate anomalies, right? So these are the four things that we do. I'm just gonna quickly go through the data. I think the important thing from this slide to pick up is that we are at a point where we have to combine spatial data with economic data, which is, you know, not super easy. Ideally, we would like economic information to come at a very low resolution, but this is not the case for most of the variables that we need. And so we have to aggregate. While all the spatial data that we use and other socioeconomic data are grids, right? So they have different resolutions, but they're all grids. The economic information which we use, which are the gross value added in agriculture, employment and losses, capital formation, all for the agricultural sector, they're not available as a spatial grid. So we take the lowest level available, which is the NUTS3 level, administrative level, which is basically provinces, Italian provinces. And we take all these spatial data and we aggregate them at the NUTS3 level after we build our index, right? So first we build our index at the grid level, then we aggregate it at the NUTS3 level in order to match all the information we have with the economic variable of interest. The data we use are pretty standard. The dataset we use are pretty standard. We use dataset from Copernicus for air pollution. We use some elevation dataset. The forest landscape integrity index is a very fine grid of 300 meters and 300 meters. The same is the mean species abundance indicator, which I will talk about it later. The largest is the number of threatened animal species, but yeah, they all come in grids. So this to give an overview of the beginning of the paper. Now we'll spend some time talking about how we built our index and what we were trying to achieve with this index. We start from the mean species abundance indicator. We start from this because this is an indicator that has been used extensively in the literature to measure the level of biodiversity that is remaining in a given area. It's the one that has been used by the European Central Bank in this paper, Woldie and co-author, and Giacomo and co-author. And we take it from an integrated assessment model called Globio. as an integrated assessment model at the global level, which calculates mean species abundance using, evaluating human pressures, evaluating several human pressures on a specific area, and they consider the most relevant drivers of biodiversity loss, which are land use change, climate change, infrastructure, pollution, and hunting. Unfortunately, Globio, or at least we couldn't find it. If you have hints on where to find them, it would be super useful. They do not have time variation, right? They only provide data for 2 years, the 2015 and 2050. So we cannot really build a panel, which is what we would like, ideally is what we would like to do, but we have to rely on 2015 data. The nice thing, on the other hand, is that for 2050, there are several shared socioeconomic pathways scenarios. So one is interested in scenario analysis, you can get this data and then try to project in the future what can happen. The problem is that the other component of the index are not, they don't have scenarios, so it's only one component that can have a scenario. The mean species abundance, as I said, is an indicator that has been used as an indicator of the level of biodiversity remaining in a given area. And just to define it so that we all remember what it is, it's basically the number of individual of species I in a disturbed situation, in a perturbed situation, over the number of individuals in species I in a pristine situation, sum up over the number of species and divided by the number of species. So it's basically an average, right? The pressure that are used, you can see them in the picture. They're, as I said, the most relevant for biodiversity loss. Globio calculates different impacts, so they calculate what is the MSA remaining from after the pressure climate change has been applied, the MSA after nitrogen deposition has been applied, and so on and so forth, and then they aggregate it into a measure of the mean species abundance. And Globio gives mean species abundance for 2 kingdoms, plants and animals. Right? So we have these 2 measures of mean species abundance. Globio does not consider in their calculations species that are not present in the reference situation. So if there is an alien species that come because of the pressures that have been applied to the environment, that species is not getting considered in the MSA situation. You can see here in the graph that the mice are not in the reference situation and they get a value of 0, basically. Yeah.
For like frogs or species which increases, the impacted are higher than the reference. So the maximum is 1 because it should have 1.5 if we just
yes. So they say that they truncate the impact at 1. So if they increase, they still truncate it at 1. So the MSA goes varies between 0 and 1. Okay, this is the MSA. The MSA gives information about ecosystem composition, right? So it's the number of species that are in a given ecosystem. When we build our index, we follow this idea. There is this paper written by Giacomo and co-author in 2024, The Economics of Biodiversity Loss, where they hypothesized a concave positive relationship between the level of biodiversity remaining in a given area and the level of ecosystem services that are provided in that area. And this is interesting because, of course, it has diminishing returns, which means that biodiversity losses are more relevant for the provision of ecosystem services when the biodiversity levels are very low. So if you lose biodiversity when biodiversity is low, it's a catastrophe for the ecosystem services provision. If you lose it when it's actually high, it's not that bad. I mean, it's bad, but not that bad. And this speaks to the idea of these keystone species, right? So there are species that they do all the work when they provide, because when the ecosystems produce ecosystem services, there are some species that do all the work in producing these ecosystem services. It's the case, for example, for vultures in India, right? There's this very nice paper where they show that losing vultures in India, you lose the cleaning job that the vultures were doing, and you have increases in diseases, for example, because they were a keystone species, which was very relevant for this. So we want to follow this idea where our ecosystem health indicator should follow kind of like the same shape as the one that they have in the paper. As I said, the capacity of health ecosystems to provide goods and services is based on complex mechanism. We don't know much at this time, or at least we don't have data about keystone species and their specific roles in ecosystems. So we believe that preserving the original biodiversity, the mean species abundance, is crucial for maintaining ecosystem functionality. And what we do to build a measure that is not just limited to biodiversity, but gives an information of overall ecosystem health, is to combine the MSA indicator with these other two indicators, the forest integrity and the number of treated animal species. In our mind, these two indicators give an idea of ecosystem fragility. So we believe that the more pristine is a forest, think of virgin forest, right? The more fragile that environment is, because it's likely that it has been subjected to very little pressures. And this means that the moment you put pressures on these ecosystems, then they will easily collapse. And the same thing goes for the number of treated animal species. The more treated animals, the more fragile the animal kingdom is in a given area. So these two measures, we hypothesize that they give us information on ecosystem fragility. And to proxy the production of ecosystem services, and so ecosystem health, we combine these indicators using a Leontief production function, where we have two factors of production, animal and plants mean species abundance. And each of these two factors of production is augmented by the level of fragility, basically. In the case of animals, we use the augmenting factor is the number of threatened animal species, while in the case of plants, the augmenting factor is the forest landscape integrity index. And this is, we like this functional form because it captures an idea that in a given ecosystem, the production of ecosystem services is constrained by the less abundant factor. So the moment you have one plant and two animals, it's the one plant that will constrain the production of ecosystem services, right? So plants and animals act as a complement in the production of ecosystem services. And so whenever we have the same level of MSA, the less fragile factors will be the limiting one. Whenever we have the same level of fragility, the less abundant species will be the constraining factor. The sample that we work with is a sample of NUTS3 administrative regions, so provinces across 3 European countries, Italy, France, and Germany. We chose these countries because they're the biggest economies in Europe, and agriculture is a relevant sector for these countries, especially in Italy, maybe a bit less for Germany, but still relevant. The spatial distribution is shown in the map. You can see that there's a substantial heterogeneity both within and across countries in the distribution of the index. Germany within countries is fairly, it's pretty bad. Germany is doing very bad in terms of ecosystem condition, and Italy and France are doing somewhat better. And within country, you see that areas that have intense agricultural production, such as the Pianura Padana here in Italy, are not really, ecosystems are not really healthy, while mountain areas are somewhat a bit more healthy. But we're not just capturing elevation. That when we saw this map, it's like, are we just capturing elevation? Can we substitute our index with elevation? And actually, if you look at Italy, in the Apennine region, it's not green, right? So even though there are mountains there, it's not very healthy. And so also in France, in the central part of France, where it should be not very high mountains, you still see environments that are fairly healthy. We have 599 NUTS, which is our level of observation. And just to give you another idea of how the index is doing, This is just the average of the index. The yellow bar are the overall average within a given country. Again, you see that Germany is the country with the less healthier ecosystem. The green bar is the average of the ecosystem condition index inside protected areas. And the red bar is the one outside protected areas. So it's interesting to see that while France has, generally speaking, better ecosystems according to our index, the level of ecosystem condition or the health of the ecosystem in Italy is much better inside protected areas, right? So it seems that Italy is doing somewhat better work in preserving and establishing protected areas compared to the other countries. Okay, so this was description of the index. If you have any questions, or I can just continue and ask. Okay, so the next part of the presentation, I will tell you what we are doing with this index, right? So the more data part of the paper. We perform a couple of exercises. So first of all, we try to validate the performance of our index. And we do this because we are introducing the new index, and we would like to make sure that you are actually introducing something new and not something that you can just do using MSA, for example. And we do this by looking at the functional form. So we compare the theoretical functional form that we had in mind when we designed the index and what we find in the data. We do a prediction exercise where we try to predict different ecosystem characteristics using either our index or the mean species abundance. And then we compare the prediction accuracy. And then we check what kind of pressures act on the ecosystem condition index to see whether they are in line with it's written in the literature. In the main empirical strategy, we try to we estimate the elasticity of ecosystem degradation of agricultural productivity to ecosystem degradation, and we try to convert this elasticity into monetary terms to give an idea of how big in terms of money these impacts are, because we are economists and we care about money in the end. We try to solve some endogeneity issues using an instrumental variable approach. We do a quantile regression, and we try to explore a bit more the climate-nature nexus that we postulated at the beginning. So in terms of functional form, I'll show you two slides. In these slides, you will see the theoretical shape on the left and the empirical one on the right. What we do here is to compare the shapes in the empirical graph. We try to compare the shapes of the relationship between two ecosystem service provision levels and different biodiversity indices. One is our ecosystem condition index, and the other one is just the average between the MSA, the plant MSA, and the animal MSA. Right? So one could also just take a simple average between these two and see how do they look. And what we see, this is just a visual exercise, so there's nothing very structured here. Just plotting is basically a scatter plot, right, of the indices. But still, you see that when we look at primary productivity, so ecosystem primary productivity, which is the amount of carbon produced by primary producers in the ecosystem, the shape that we obtain using our index, the ECI, is somewhat closer to the theoretical one compared to the one that we will have if we only use MSA. And it's interesting because there's a little kink there, but I wouldn't say there's a significant change of convexity here. While using the MSA, you see that it's concave at the beginning and then convex, so there is a significant change in the convexity. So we're happy about this because, yeah.
Also, I was looking at the graph. Why the MSA start from 0?
That's the minimum that we have. I agree. It's different.
Just like curiosity.
Yeah. I can check the data. I don't remember. It should start. They're all bounded between 0 and 1, but probably it's it's the minimum value. Also, they don't get up to 1, right? So there's no NAS tree that reaches 1 in this sample. There are some in Brazil, for example, or other countries in Africa, but there was in Europe. It's very tough. Okay, so we are happy with this, and we are also happy with the ecosystem carbon sequestration, which is another ecosystem services that is provided by healthy ecosystem, even though here it's a bit less clear, right, whether they are significantly different or not. You still see that there is this kink in the MSA relationship, and this is much less pronounced when we use our index. So even though these are just a visual inspection of what we're doing, we are happy because the theoretical shapes are closer to what we wanted to capture. The next exercise we do is this index validation and or index prediction. Sorry. So basically here we use a random forest algorithm, and we try to predict each of the outcomes that you see in the column outcome, right? And these outcomes are, some of them are ecosystem characteristics, some of them are ecosystem services provision, so the level of the provision of ecosystem services. And we try to predict them using a random forest where we keep fixed the set of predictors that we use, and then alternatively include either the ecosystem condition index or the mean species abundance index, the average between animals and plants. We train the model on a training sample, and then we make out of sample prediction, and we calculate the root mean squared error out of sample, so on the test set. What we see is that, and the reasoning behind this exercise is that, well, if you cannot predict at least marginally better, then we are better off using the MSA, and we don't have to go into troubles creating our index. But actually what we see is that in general, there is an average reduction in the root mean squared error using our index of 1.70% compared to the case where we use the mean species abundance. And for some of these ecosystem characteristics, the decrease is fairly large. So for example, for relative fragmentation, we are much better at predicting relative fragmentation compared to MSA. And the MSA, the error changes decreases by 7%. For food and feed production and ecosystem carbon sequestration, we are marginally worse, right? But overall, we are doing a marginally better job. And the last thing we do to try to understand how does our index work is to try to test what kind of pressures act on the ecosystem index. Here, I'm presenting the regression coefficients, right, of a regression where the dependent variable is our ECI, and these are the regressors that we include in the regression. There are the graph is showing point estimates and 95% confidence bands. And you can see that basically nothing matters except for land use variables, right, and marginal population density. So the percentage of NUTS3 area, which is under cropland, is negatively and significantly correlated with the level of our index. So the more cropland you have, the worse ecosystem condition is. Same goes for urban area share, while for the share of area under protected status, we have a positive correlation, of course, which makes sense. We were a bit puzzled by the fact that pollution doesn't really do much, and we are trying to understand why this is the case. I think one of the reasons is that we're having a cross-section, so we don't have the time dimension. And the other reason is that here we're not using cumulated emissions, we're using just yearly averages, right? So it's likely that if we look at cumulated ones, it will be much different. Okay, so we validated the index. It seems, I mean, at least for me and for us, maybe you're not convinced, but I hope so. It's doing okay, and is also providing a bit more information compared to the mean species abundance one that the literature has used so far. Now we go to the estimation of a production function. We estimate this equation. On the left-hand side, we have the logarithm of the agricultural gross value added per hectare of cropland. And on the right-hand side, we have factors of production, so labor and capital used in agriculture, and our measure of ecosystem condition loss, which is defined as 1 minus ecosystem condition index. And so it's the opposite. We include a bunch of covariates in the regression. We test different models, right, to see what's the sensitivity of the coefficient when we include more or less regressors in the analysis. We have to calculate capital. We don't have capital available at this level of disaggregation. We only have gross fixed capital formation, which is investment. It's a measure of flow. So we have to calculate the stock of capital instead, and we follow this Van der Donk and Coulter approach. We add country fixed effect and we cluster standard errors at the NUTS2 level, so one level up compared to our unit of observation. And the coefficient of interest is alpha, which tells us the productivity elasticity to the environmental quality degradation. This is basically a Cobb-Douglas log linearized, right? It's very simple, but we're now trying to experiment with different production functions as well to see whether the results are consistent. And these are the main results of the paper. So again, point estimate and confidence band, this time 90%, for the three main variables that we're interested in. Starting from the bottom, the base plus ECI loss model is a regression that only includes ECI loss, capital, and labor, and country fixed effects. So it's the most simple model you can think of. We find the negative elasticity when it comes to ECI loss. This is around 0.3, minus 0.3. And good coefficients for factors of production. If we go up one line, we add to this specification also climate variables. So we define climate anomalies as the long-term, the deviation from the long-term mean of temperature and precipitation to capture chronic climate risks. And again, the coefficient is fairly stable and also again in the range of minus 0.3. We also try to add variables that tell us what is the contribution of ecosystems to crop pollination, right? Because we would like to capture something more than pollination and to have more of a holistic measure of ecosystem condition. So we add that to the regression, and that doesn't really make a large difference. So we are confident that this is we are in the coefficient. Our coefficient of interest is fairly stable across specification. So we have a negative elasticity of minus 0.3, right? What do we do with this is to try to put a value to these losses. So we using it's very simple algebra using the formula of elasticity. We just input a shock and then we calculate the response, right? Of course, we make a lot of assumptions here that the relationship is linear, that the elasticity is constant along the curve, and so on and so forth. But this is just interesting to understand what might happen. And actually, following one standard deviation shock in the condition of the ecosystem, so a loss equal to one standard deviation, we find sizable effects on the agricultural gross value added per hectare of cropland. And if you look at Italy, for example, compared to an average of agricultural productivity, which is about $2,000, we find a decrease of around 10%. So that's fairly large. And so these findings, of course, highlights the fact that ecosystem preservation might help sustaining agricultural productivity and rural livelihoods. We are a bit concerned about endogeneity, and one of the things we are concerned the most is the fact that we don't have time variation in the data set because we have a cross-section. And this is an issue because it's likely that time-varying shocks shape the path of ecosystem condition and agricultural productivity in a given NUTS. So what we try to do is to solve this problem by instrumenting ecosystem condition loss using morphological characteristics of administrative area, which should not vary over time. So we use average elevation, average ruggedness, which we calculate at the grid cell level, and their interaction as instrument for ecosystem condition index loss. To try to soften the concerns about the fact that the exclusion restriction doesn't hold, that there is a direct effect between morphological characteristics and agricultural gross value added, which doesn't pass through our index, we calculate these values on cells with natural length-over. So we exclude cropland cells and UFM cells. The result, and then we use a standard two-stage least square specification. In the first stage, we predict our explanatory variable with the instruments, and then we use the predicted values to run the main regression. What we find is a coefficient that is much larger compared to the non-IV cases. So this is around minus 0.9, so it's very close to minus 1, but also confidence bands which are fairly large, and they do cover the previous estimates. Interestingly enough, though, the coefficients on factors of reduction are super stable, which is very good. So I will go a bit quick now because I only have 15 minutes. This is the result of the quantile regression. So for each quantile of the outcome distribution, we estimate the elasticity. And not in an IV setting. We couldn't find a way to do it in an IV setting. We estimate the elasticity and we look at the distribution of the effect with respect to the distribution of the outcome. So you can see that on the left part of this graph, the coefficients are not different than 0. So that means that at low levels of agricultural productivity, we don't find an effect of ecosystem degradation on agricultural productivity. The effect materializes at higher levels around the third quintile and fourth quintile, and then it stays quite stable. So basically, this tells us that it's the capital intensive and labor intensive areas, so places where agriculture is heavily mechanized that have high productivity, which suffer the most the moment ecosystems get degraded. And finally, we try to look at the nature and climate nexus. So what we know from the literature that there are some nature-based solutions which could work in sheltering the economy from damages from climate change. And one example is mangrove forests, which reduce damages from flooding and preserve ecosystem, which prevent coastal erosion. So we want to test this hypothesis. And what we do is to, instead of using the continuous variable ECI loss, we calculate quartiles of the ECI loss distribution, and we interact these quartiles with climate anomalies, temperature and precipitation anomalies, right? So in this equation, QI is equal to 1 if the value of ECI loss is within a given quartile, within quartile I. And everything else is defined as the previous equation. So we have the same controls and the same factors of production and so on and so forth. What we see is this graph. We see that what happens is that the moment your ecosystem is fairly healthy, so you are in the first quartile of the ecosystem condition index loss distribution, temperature deviation does not have a sizable effect on agricultural productivity. The moment we go up and the moment our ecosystems become more and more degraded, so we are in the fourth quartile, temperature deviation has a large effect on agricultural productivity. And actually, it's interesting to see that the moment we don't include temperature deviations, right? There is a strong positive relationship between ecosystem degradation and agricultural productivity, which is in line with the fact that usually ecosystems are destroyed to make space for new cultivation and new agricultural land, right? So you wouldn't do that if there was no productivity advantage doing that. But the moment you are hit by a temperature shock, for example, then this effect disappears. We don't find the same for precipitation, though, so we are still trying to understand why this is the case. Okay, so I think I rushed through it enough, and I'm done. Thank you very much for listening, and then back to after this.
Thank you, Stefano, for being in time, most importantly, for the interesting and comprehensive presentation. Now the session is open for questions and answers.
Ask first if there is a question.
Okay. We have decided to begin with those who is online. If you have questions, is there any question on the chat? Cindy put it. Okay, maybe she has raised her hand. Cindy, do you want to comment? Thank you very much.
Hi, yes. Thank you so much. Do you hear me well?
Yes,
Yeah.
yes.
Okay. Yeah, Stefano, thank you so much for your presentation, and the work in general is really interesting. And I think you address one of the problems with previous work is that they only use one indicator of biodiversity or no indicator of biodiversity. So in that sense, I think it's it's a contribution what you're doing with the aggregating several in the index. However, I'm a little bit concerned with the, I think when you show graphs, how they compare the theoretical versus the empirical one. In particular, I don't have the slide number, but the one that relates the biodiversity index with the primary productivity.
Yeah.
So there are two components. The first is that in the first part, when the ecosystem is pristine, say like this, you're losing and you increase the biodiversity index. If I'm reading this correctly, this means you're destroying the ecosystems, and you have an increase in productivity. So in the first part of the graph, the left.
I'm gonna try to share it again.
Yeah.
Page 17, 16, I guess. 16. Line 16.
So this one, right?
Yes. So in the first part, you see that your biodiversity index, I'm assuming it is not starting 0 or in 0.1, but my point is, as you see, you go from 0 to 0.2, you're increasing productivity by losing ecosystem condition, if I am reading the graph properly.
So this is not the ecosystem condition loss. So it's not 1 minus ECI, it's pure ECI. So here, moving from left to right, we are improving the ecosystem condition.
Okay, so then it goes the other way. So why, when you get from 0.7 to 0.8, then you lose productivity if you have more
Yes,
intact ecosystem?
kind of bent, yeah.
Yeah. So that's what worries me is a little bit, and also the fact that at some point, I mean, if the ecosystem has complete collapse, productivity should be 0. No.
Yes.
You have no ecosystem. So those are my two main points here. And this also connects with the assumption in the Cobb-Douglas. I mean, I know that it's mathematically convenient, but in a sense, by having a Cobb-Douglas production function, you're assuming substitutability between labor, capital, and the ecosystem condition, right? But it doesn't consider that if there is no, if ecosystem have fully collapsed, there should be no production. So these two things are kind of connected.
Yeah.
That was the comment. And maybe the questions I have are I didn't get the spatial resolution that you finally were able to calculate for the index, and also for the regression that you did at the end.
Right.
Not at the end, the one that relates productivity, agricultural productivity, with the ecosystem condition.
Yeah, thanks a lot. These are two very good points. Coming just 1 second back to the first comment, you're absolutely right. We don't have that. The moment ecosystem completely collapse, the level of primary productivity is 0. It's very tough to model these tipping points, right? So we should be able somehow to try to include the fact that these things are very much non-linear, and there is a point after which ecosystems completely collapse, and then there's no production anymore. And I think this is one of the issues why we are interested in these things, and we think about ecosystem loss, and usually we don't consider the fact that the moment ecosystems are gone, nature is gone, the whole economic activity is going to be gone. It's like, right? So there's this kind of thing that we have to consider. For the resolution, the index is calculated at the 1 kilometers times 1 kilometer resolution. But then, because we have the economic variables at the NUTS3 administrative level, we have to aggregate it at the NUTS3. So the level of observation in the regression is the NUTS3 administrative level.
Okay. How were you able to have the index on a 1 by 1 if your number of threatened species is at 30 by 30?
Yeah, so we split the squares, basically. We assume a constant level of the number of threatened animal species within that square, and we assign it to each of the smaller square that we do the splitting. Yeah.
Okay. And yeah, sorry, my last question will be, as you mentioned, the MSA is for a specific SSP, so I'm wondering at the end, which scenario did you use?
For the historical ones is not
Okay.
not scenario dependent. Yeah, it's
Okay,
just the
okay.
one in the projections that are there's 3 SSPs.
Okay, okay. Thank you so much. Great work.
Thank you very much. Maybe related to that is 2015 MSA from GloBio. Is it observation data or is also model data?
It's modeled. Right? So it's modeled, but also because I got so my understanding of the MSA, but I mean I'm an economist, not an ecologist, so is that you always have to compare to make some sort of counterfactual analysis, right? So I guess it has to be part of coming from a model. Is it is the baseline? So the reference situation is historical. The use historical land use data from 2000, I think, but then the counterfactual is.
Okay, great. Anyone? Any additional question? Gabriela, can you ask directly, or I have to read out your questions?
Yeah, unfortunately, I am in a quite loudy place because of I couldn't be there. So maybe if you could please read them, would be fine. But as I told, I am already in contact with Giacomo, so maybe are I don't know, quite long questions to be answered, so we can also discuss them privately if you prefer. Thank you.
Okay, thanks for the questions. Maybe I just read out. If you can, you
sure.
can reply. The first one is like about the ecosystem condition, ECI. Since you use an empirical approach on specific few well-documented countries, why you relied on model-driven data plus GloBio for the ecosystem integrity and species, which don't capture the real-world and local scale pressures on ecosystem due to agricultural practice and then agricultural pressures, instead of using, for example, from Natura 2000 or any other empirical data. That's the first question. The second question is also my question, more or less. Agricultural gross value added data, or GVA, is derived from our DECO data at NASCHA, which is a very aggregate agricultural sector, which aggregates agriculture, forestry, and fishing. You said that agricultural product is defined as at NUTS level 3, and it's also per cropland, agricultural value per cropland. Then divided by NUTS cultivated area or cropland. I would like to understand if these two metrics are comparable, GVA and cropland area, because the GVA is at NACA level, since forestry and fishery do not concern in the cropland. But in my case, I would also say livestock. Of course, I know one of the indicators in the working paper covers also managed pasture land, but just maybe with clarification about that. The third is regarding endogeneity and causation problems. Have you tried using quantity productivity measures, tons per hectare, as a control, or GVA is given by the market dynamics as it's impacted by also market price and consumer preferences?
Yeah.
Thank you, Gabriela.
Thank you. Okay, I'll try to answer. So to the first question, I think, Gabriel, you're absolutely right. So I was not aware of these this data set, so we can definitely try actually. But if you're already in contact with Giacomo, then I guess you already wrote the name of the data set to him. Thank you very much for that. I think it would be better. We tried a couple of other sources. We looked at the WF, for example, which create this Living Planet Index. They have geospatialized samples, right? So we can look at those samples. I think we use MSA from Globio because it's very convenient having the grid, right? And you don't have to interpolate because from the WWF, you have locations with number of animals and number of individuals. We had an issue because there were a lot of different units of measurement and we didn't know how to aggregate these numbers. And on top of that, you don't have the grid, right? So you just have points in space. But thank you very much for suggesting other data set. For the, sorry, the second question.
The second was like comparability between the GBA, which is
Okay,
an
right.
FBA,
Okay, yeah. So that's also very true. It includes forestry and fisheries as well, but it's the most disaggregated data that we could find. So I don't think we can access just agriculture at this NUTS3 level of disaggregation. So we have to rely on that. For cropland, so it's not cultivated land, so we don't use the amount of cultivated land. We take the Copernicus land classification, and we take all the grid cells that are either cultivated or suitable for cultivation. So the ones that have classified as suitable for cultivation and pastures as well.
Yeah.
And then we aggregate it at the NUTS3 level, and as well as we sum them up. Yeah, the size of the square, so we can calculate how much it is in a given month. We could try a different approach to see whether other type of land classification exists, but to disentangle pure agriculture from forestry and fisheries, I think it's a bit complicated because we don't really have that data.
Faden has now the farmer as well count.
Right.
It has
We should check FAO. I think at some point we did, and yeah. And the last question about endogeneity, yes. So we are trying to do two things now. I think using quantities instead of values is a bit of an issue because we would have to aggregate kilos of potatoes with kilos of maize, and those are two different things. So it's easier for us to have a monetary measure because it's all expressed in the same, it's all euros, and I think it's better. We tried at some point to do kilos per hectare of cropland, but we had this issue. The second thing is that I agree that there's a lot of objections that can be made to the exclusion restriction, right, which is fundamentally untestable. And we are trying right now to understand whether it has a price effect. So one idea we had was that areas with high elevation and high ruggedness are harder to reach, and they might be less integrated with global markets and also local markets. So we are trying to see whether we can create some sort of road network which tells us how integrated these areas are. This could be another channel through which there is a change in gross value. So we're trying to address this.
Yeah.
Well.
Anyway, Gabriel, as he said, is also
Yeah, exactly.
we'll
Right,
continue the discussion. Maybe now I bring the questions to the floor here. Maybe. Questions to okay.
A little bit closer to the mic.
So that everyone can hear
better.
Okay.
Wondering a bit about what you want to model in the future. You were mentioning mangroves, which is not really very pertinent for the geophysical area you have taken into consideration. What else? Which else of measures of ecosystem integrity do you want to use? Measures of adaptation?
Thanks for the question. Yes, I agree. Mangroves are not relevant for Italy and Germany and France. But they are the components of an ecosystem which do provide a service to the economy, right? Because it's really, there's a lot of evidence that says that mangroves are very effective in reducing flooding.
No doubt about that, but how do you want to get this into your model?
No, we're not gonna get that into our model for sure. We are trying now to explore different biodiversity measures as well. So one that is actually data-based is or more empirical, is the IUCN red list, for example, which also comes as a grid. So this is something we're trying to do, and that would also allow us to have a time dimension, because the IUCN red list is something that we observe over time. So one concern we have right now is to try to find something that will give us a time dimension, because we're very concerned about this, and having a panel would solve a lot of our issues. In terms of integrity, so other measures, we don't have anything in mind right now, but very happy to have suggestions if you think something is relevant.
Any other questions from here? Any other questions? Okay, no other questions, no online. Lots of thank yous. Okay, lots of
Thank you.
appreciations.
Thank you very much again.
Okay, then we close the session. Thank you again for being here. It's also our second presentation from colleagues from Prometeia. Last year we had also from Professor Lorenzo Forni and Dr. Elena Giardina on energy performance certification. We are happy to host if you have similar topics which we share commonly, and we welcome you again in the future. Hope to see you again, and thanks for today for the presentation, for your time. Thank you.
Thank you very much.